Bismillahirrahmanirrahim. Hi everyone, I hope you are all doing well. I welcome you all in class of real analysis. My name is Azmat Ali and we are discussing chapter number 3, Numerical Sequences and Series. In this short video, I will discuss first 3 questions from exercise 3. This is question number 1. That is related to the convergence of sequence, and I hope you are familiar with the definition of convergence of sequence. However, we revise it once again. We say a sequence Sn is convergent and it converges to the limit L if for every positive real number epsilon, where epsilon is a real number, there exists a positive integer n naught such that the absolute difference of this sequence Sn from its limit L is less than this epsilon whenever your n is greater than or equal to n naught. So this is the basic definition of convergence of sequence that I have discussed in my previous lectures, and I hope you are very well familiar with this definition. In question number 1, we have to show that prove that the convergence of the sequence Sn implies the convergence of Sn absolute. That is, this says that if Sn converges, then Sn absolute also converges. Suppose this converges to limit L, then its absolute value also converges to the limit L. Is the converse true? Next we have to show that it is true that if this sequence converge, then absolutely, then without absolute it also converge or not. Further, here in case of absolute, this will converge to L absolute, but still we have to just show that it is a convergent sequence. Suppose that the sequence given sequence Sn converges to the real number L, then by definition for every positive real number epsilon there exists a positive integer n naught such that by definition the difference of this sequence from its limit is less than epsilon whenever your n is greater than or equal to n naught. Since we have an inequality and this inequality hold for every real number, the absolute of Sn absolute minus L is always less than Sn minus L. You can check this hold for any real number. So this inequality hold as Sn minus L, this absolute is less than epsilon. So by using transitive property, the first inequality is less than this and this also less than epsilon. It implies that this number Sn absolute minus L absolute is less than epsilon whenever your n is greater than or equal to n naught. And what does this show? This shows that the inner number, this Sn absolute, has a limit L, that is, this converges to the limit L. Converse of the statement is not true in general. For example, if we take the sequence Sn is equal to minus 1 whole power n, then Sn does not converge because it keeps oscillating between minus 1 and plus 1. I mean to say, if you find here the first term is S1 is equal to minus 1, your second term is minus 1 square, that is equal to plus 1. If you find its third term, the third term is minus 1 whole cube, that is minus 1. So for every even power, the term of the sequence is positive 1, and for odd exponent this is equal to minus 1. So this shows that the terms of the sequence oscillate between the number minus 1 and plus 1. It shows that this sequence does not converges because it has two limits, minus 1 and plus 1. But if you take its absolute, that is minus 1 whole power n absolute, so this gives only plus 1, that is its absolute is equal to plus 1, because you have seen that minus 1 whole power n is either plus 1 or it is minus 1. So whenever you take absolute, this is equal to plus 1. So its absolute sequence is just equal to plus 1. That is the constant sequence. First term is 1, second term is 1, third term is 1. This is a constant sequence. And the constant sequence converges to itself, so its limit is 1. So we can see that the sequence converge absolutely, but without absolute the sequence does not converge. So convergence of Sn absolute does not implies convergence of Sn. The next question is a very elementary question, and this is from calculus level question. In this question we have to just calculate the limit of this expression. It is not required that we have to find the limit by using delta epsilon, by using epsilon definition. So we have to just evaluate the limit. I have written that if we take n square common from the square root, then apply the limit, it gives us 0 into infinity form, that is the indeterminate form. So firstly we will rationalize the given expression. So I will multiplying and dividing the number square root n plus 1 plus n. By using the algebraic formula a minus b into a plus b over the numerator, this gives us a square minus b square. So this is my a and this is my b. So according to this formula, when you apply this formula over the numerator, this becomes equal to n. Now we apply limit, but just firstly we take n square common from the square root. So when you take n square common from the square root, this becomes 1 plus n over n square whole square root. By separating the square root, this becomes n square whole square root into 1 plus 1 over n. As your n approaches to infinity, and this infinity is from the positive side, so this is equal to plus n. If here your limit is minus infinity, then this square root will be equal to minus n. So this is equal to n. So that n will be cancelled from with this n, and this gives us 1 over 1 square root 1 plus 1 over n plus 1. Now when you apply limit 1 over infinity here, 1 over infinity, this approaches to 0, this becomes 1 plus 0 plus 1, that is 1 by 2. So the limit of this expression is 1 by 2. Question number 3 is somehow this is a challenging question. This question says, if the first term of a sequence, this is a recursive sequence, a recursive relation between the terms of the sequence. The first term of the sequence is S1 is equal to square root 2, and Sn plus 1 is its n plus 1 term is given by square root of 2 plus square root of Sn. And this sequence holds for every positive integer n is equal to 1, 2, 3, so on. We have to show that Sn is convergent and Sn is bounded by 2 for n equal to 1, 2, 3. Okay. Here we will use monotone convergence theorem, which says that every bounded monotonic sequence is convergent. So according to this theorem, I will show the two conditions. First is boundedness. So firstly I will show Sn is bounded, and then I will show that this is a monotonic sequence. So my target is to show this is bounded plus monotonic. And for boundedness, I will show that this is less than, its every term is less than 2. And for monotonic, I will show that this is a monotonically increasing sequence. I hope you have information about boundedness and monotonic. So firstly we show that the sequence Sn is a bounded. Here the first term is S1 is equal to square root 2. Clearly you know square root 2 is always less than 2. Now next, what is S2? S2 will be, this is my sequence given by Sn plus 1. If you put n is equal to 1 here, this becomes n is equal to 2, this becomes S2, that is the second term, and here this becomes S1. So your S2 is given by square root of 2 plus square root S1. I have to show that this term is also less than 2. Mean to say your S2 is also less than 2 here. For this, firstly I will evaluate this expression. We will check whether this number 2 plus square root S1 is less than 2 or not. Here S1 is less than 2. We have see here S1 is less than 2. When you take square root of S1, this becomes square root of S1 less than square root 2, and square root of 2 is less than 2. This implies square root of S1 is less than 2 here. Now adding this 2 on both sides. So when you add 2 here, this becomes 2 plus square root S1, and by adding 2 here, this becomes 2 plus 2, 4. So the number inside the square root, main square root here, this number 2 plus square root S1 is less than 4. Now I will take square root on both sides. So this becomes S2 is equal to square root of 2 plus square root S1. This is less than 2. This shows that S2 is less than 2 here. Continuing this process, we can show that this sequence, every term of this sequence is less than 2 for every positive integer. This shows that the sequence is bounded by 2. We say that a sequence is bounded. Suppose I have a sequence Sn. A sequence is called bounded if its every term is less than some positive real number m. Some positive real number m, where m is positive. Then we say that this sequence is bounded by m. And here we can see that this sequence, that is the sequence of positive terms, is less than 2. So this sequence is bounded by 2 here. Next I will show that this sequence is a monotonically increasing sequence. So for monotonically increasing, I will use a mathematical induction. Next, by using induction, we show that the sequence is monotonically increasing sequence. You know that the induction use the 3 steps. The first step is base step. Here we check the statement is true for n is equal to 1 or not. For n is equal to 1, this is simply given. S1 is equal to square root 2. This is already given. So I will evaluate the next term S2 also. And because I have claimed that the sequence is monotonically increasing, so I will show that S2 is greater than S1. A sequence is called monotonically increasing if every next term is greater than the previous. That is, it should follow this chain. S1 should be less than S2, S2 should be less than S3, up to so on. Then a sequence is called monotonically increasing sequence. So we will evaluate here the next term S2. What will be the S2? S2 is given by square root of 2 plus square root S1. My target is to show that S2 should be less than S1. S2 should be greater than S1, sorry. By putting the value of this number square root S1. What is S1? S1 is square root 2. So when you put here S1 is equal to square root 2, this becomes square root of square root 2. Now we have to check about this expression. Can you say that A number is equal to itself, that is 2 is equal to 2. Yes, clearly a number is equal to itself. So now by adding this number square root of square root 2 on the left side, either on any side you can add. So if you put add this number on the left side, then clearly this number is because of positive. So when you add this number with 2, this side becomes bigger than 2 here. Now taking square root on both sides to make this form, this becomes greater than square root 2. What is this? This is my S2 and this is S1. This shows that S2 is greater than S1. So the statement is true for the base step, that is for n is equal to 2. Next step is inductive hypothesis. This is second step in the induction. In this step, we suppose that the statement is true for n is equal to k. That is, we will suppose sk plus 1 is greater than sk. That is, k plus 1th term is greater than its kth term, where k is a positive integer, where k plus 1th term is given by this formula, square root of 2 plus square root of sk. This is my last step, third, inductive step. In this step, we will show that the statement is true for also for n is equal to k plus 1. Statement for n is equal to k plus 1 will be, what is our formula of Sn plus 1? Sn plus 1 is given by square root of 2 plus square root Sn. When you put n is equal to k plus 1 here, this becomes sk plus 2. And when you put n is equal to k plus 1 here, this becomes sk plus 1. So the k plus 2 term is given by this number. My target is to show that this term is greater than, should be greater than its k plus 1 term. I will use the inductive hypothesis that says sk plus 1 is greater than sk. This is my assumption. Now I will make this form. According to this form, I have to take the square root of this term, sk plus 1. So taking square root on both sides, this gives. Now I will add 2 on both sides. So when you add 2 on both sides, this becomes 2 plus square root of sk plus 1, 2 plus square root of sk. Lastly, we will take this whole square root. So by taking whole square root on both sides, this gives. What is this? This is our k plus 2 term and this is our k plus 1 term. This is our k plus 1 term, this is our k plus 2 term. Hence, by induction statement, statement is true for every positive integer. Hence, this sequence is monotonically increasing sequence such that your sequence is bounded by these two numbers. This is upper bound, this is lower bound of this sequence. Hence, the sequence is convergent. Because to show its convergence, we have to just show this should be bounded and this should be monotonically increasing. So we have proved both of the conditions. Hence, by monotone convergence theorem, this sequence is convergent. Further, according to the question, there is no requirement to find the limit of this sequence. It is not requirement. So there is no requirement to find this limit. Although if you are interested to find the limit of this sequence, it can be found very easily. But suppose that its limit is s, because when a sequence is convergent, then clearly it will have a limit. Suppose this sequence has a limit s. So when we apply the limit n approaches to infinity on both sides, here and also in the square root, when you apply limit here, because when you say a sequence has a limit s, then its n plus 1th term and its nth term both has limit s. So you will replace this expression with s and this will also replaced by s. Now taking square on both sides, this becomes s square is equal to 2 plus square root s. And again, if you take square on both sides, this becomes s square minus 2 is equal to square root s. Now taking square on both sides, this becomes s raised to power 4 plus 4 minus 4s square minus 4s square minus s is equal to 0, and this is fourth degree polynomial. And to solve this, you can use Newton-Raphson formula or any other numerical approximation. That will be difficult. That's why I think in this question there is no requirement to find the limit of this sequence. I hope today's lecture is very helpful for you. If you find this lecture helpful, please like, share and subscribe my channel. Inshallah, in the next lecture we will discuss from question number 4. Take care, Allah Hafiz.